So we have seen the use of draft tube in the last lecture. Okay. So mainly you should understand that draft tube, because of the draft tube you are able to create the negative head at the end of the runner of a reaction turbine. Because of that negative head, the pressure difference, okay, it becomes more. Okay, suppose there is a inlet pressure of 50 meter of water and outlet pressure is 1 meter of water. 1 meter of water, then the change of pressure, it is 50 meter minus 1 meter, that is the 49 meter of pressure head difference you are using for producing the power. This is the net pressure head difference that you are obtaining. Okay, but suppose instead of 1 meter at the outlet of the runner, you are getting as a minus 1 meter reading, okay, at the outlet. That is the negative head at the outlet. Inlet is 50 meter and outlet is minus 1 meter. So the net head, that is nothing but your pressure difference between inlet to outlet, that will be now 50 minus of minus 1. So it will become 50 plus 1. So 51 of meter. So initially when it was plus 1, you were getting the pressure head as 49 meter. Okay, now when it is becoming negative minus 1, you are getting 50 plus 1, that is 51 meter. So 2 meter of head you are getting extra for producing power. Okay, so net head is increased because of this negative head. So that is the use of negative head establishment because of the draft tube. So that you remember. Okay, so by using draft tube, the net head on the turbine increases, the turbine develops more power and also the efficiency of the turbine increases. If a reaction turbine is not fitted with a draft tube, the pressure at the outlet of the runner will be equal to atmospheric pressure. It is equal to atmospheric pressure. The water from the outlet of the runner will discharge freely into the tail race and the net head on the turbine will be less than that of the reaction turbine fitted with a draft tube. Okay, so if you are not fitting draft tube, you are getting less net head. But if you are fitting draft tube, because of the negative head created, you are getting more head, net head. Okay, and that will increase the power. Now there are some types of draft tubes. Okay, let us see quickly which are the different types of draft tube. So this one is called as a conical draft tube. It is the most widely used type of draft tube. Okay, so as we see that the draft tube function is to, because it is decreasing the pressure. Okay, negative pressure you are getting here. Okay, at the outlet of the runner. Okay, so it is the inlet of the draft tube is nothing but outlet of the runner. So negative pressure means your pressure decreases. That's why velocity increases. So velocity is increased. So you are giving some increasing area to increase this velocity. So velocity will to decrease the velocity. Okay, so here velocity is maximum. So you are reducing the velocity. So pressure is recovered, and that negative pressure, when it enters into the tail race, it becomes positive pressure, so that there should be no suction or no vacuum at this point also. So that negative pressure utilization is done at runner end, but we have to supply this water at atmospheric pressure anyhow, okay, to the tail race. So that's why it is negative pressure is converted to positive pressure. So this is a conical draft tube. Then there is a simple elbow type draft tube, then moody spreading tube. Okay, these are the types of draft tube. This is again a draft tube with circular inlet and rectangular outlet. Okay, so this is one of the draft tube. So these are the types of draft tube that you have to remember. Then draft tube theory. I have told you, you are getting the negative head at the inlet of the draft tube. So how you are going to judge, or how you are going to justify that this is a negative head? So we are going to apply Bernoulli's equation between this point and this point, and we are going to see whether the pressure at this point is the negative or positive. Okay, so draft tube theory. Now let us see. Okay, this is HS. HS is nothing but vertical height of draft tube above tail race level. Okay, and draft tube is slightly inserted inside the tail race. Okay, the distance of this is called as y. Y is the distance of bottom of draft tube from the tail race. So draft tube is slightly kept inside the water. Okay, so this is the distance y. So we are going to apply Bernoulli's equation between the outlet of the runner and the outlet of the draft tube. So outlet of the runner is 0.11 and our outlet of the draft tube is 22. So here you see the pressure is P1 and here the pressure is P2. So let us see the application of Bernoulli's equation. P1 by rho g plus V1 square by 2g plus Z1, okay, is equal to P2 by rho g plus V2 square by 2g plus Z2 plus HF, that is the loss across this draft tube. Okay, so if you see P1 by rho g plus V1 square by 2g plus Z1 will be HS plus Y. Z1 will be HS plus Y. If you take reference as a 2-2 section, then Z1 will be HS plus Y, and P2 by rho g as it is, V2 square by 2g as it is, plus Z2 will be reference, so it will be 0, and HF is the loss of head. Okay, so if you simplify, now this P2 by rho g, if you see P2 by rho g, this is the pressure. Again, if you apply the Bernoulli's equation between this this tail rest level and this draft tube outlet, again if you apply Bernoulli's equation in this both points, okay, if you see instead of applying Bernoulli equation, if I say you are applying the hydrostatic law, that means the pressure at this point and the pressure at this point. If you see, this is the height y, okay, so the pressure at this point is atmospheric pressure, and the pressure at this point, it will be greater than atmospheric pressure, right? So it will be PA by rho g plus y. So P2 by rho g will be nothing but PA by rho g plus y, so that will be the pressure increment at point P2. So P2 by rho g is equal to PA by rho g plus y by hydrostatic law. So that's why we can replace P2 by rho g by PA by rho g plus y, and substituting this value of P2 by rho g in above equation, we are getting the P1 by rho g plus V1 square by 2g plus HS plus y is equal to P2 by rho g, you can write as PA by rho g plus y plus V2 square by 2g plus HF, and if you simplify this, y will get cancelled. Okay, P1 by rho g plus V1 square by 2g plus HS is equal to PA by rho g plus V2 square by 2g plus HF, and P1 by rho g, our aim is to find P1 by rho g. So P1 by rho g is equal to PA by rho g plus V2 square by 2g plus HF minus V1 square by 2g minus HS. Okay, so P1 by rho g is equal to, if you rearrange these terms, all the terms, you will get PA by rho g minus HS, you take first minus all these terms, if you take inside the bracket, it will be minus V1 square by 2g minus V2 square by 2g, minus it will become plus, okay, and minus HF, okay, again minus of minus, it will become plus. So if you see this equation carefully, P1 by rho g is coming less than PA by rho g, so it is coming less by this value, HS minus the value in the bracket, that will be the value which you should subtract from PA by rho g to get P1 by rho g. It shows that P1 by rho g is less than atmospheric pressure. P1 by rho g is less than atmospheric pressure, and hence it is a negative pressure. So pressure at point P1 is, or at section 1 is negative pressure or less than atmospheric pressure. There is one more important point in the numericals. It is asked efficiency of a draft tube. What is efficiency of draft tube? So as we have seen, across the draft tube there is a friction. Okay, friction loss HF. Okay, so if you consider that friction loss, then you will come across the term efficiency of the draft. So efficiency of the draft tube is nothing but its function is to convert this kinetic energy, okay, into pressure energy. So whatever is the kinetic energy, your actual conversion of kinetic energy into pressure energy to the theoretical kinetic energy at the inlet of the draft tube. Okay, so actual conversion means, if because of friction no kinetic energy, some loss will be there, that kinetic energy will not be converted into pressure energy, so that loss you have to take into account. So conversion, actual conversion of kinetic head into pressure head, it is V1 square minus V2 square by 2g, that is the conversion, okay, minus the loss, okay, minus loss, so that will be actual, okay, divided by the kinetic head at the inlet of the draft tube. Actually in some books it is taken as V1 square minus V2 square upon 2g. V1 square minus V2 square means the draft tube efficiency is given by V1 square minus V2 square upon 2g minus HF upon V1 square minus V2 square upon 2g. Okay, so this HF is taking the loss into account. So but now in this we have to follow the kinetic energy at the inlet, that is nothing but V1 square by 2G. So this is the formula you have to remember, that the efficiency of draft tube is given by V1 square minus V2 square upon 2G minus HF upon V1 square by 2G. So let us see numericals quickly. A water turbine has a velocity of 6 meter per second at the entrance to the draft tube and a velocity of 1.2 meter per second at the exit, right? It's to convert the kinetic energy, so kinetic energy decreases. For friction loss of 0.1 meter and tail rest water 5 meter below the entrance to the draft tube, find the pressure head at the entrance. Okay, so P1 by rho g you have to find. Obviously it should come negative. Okay, so let us take V1 as 6 meter per second, V2 as 1.2 meter per second, HF is equal to 0.1 meter, that is given the loss, and 5 meter, it is the tail rest level from the entrance of the draft tube. So HS is given as 5 meter. Okay, the formula HS is given as 5 meter, and this is Y distance. Okay, that Y distance you have to consider according to our theory. So if you apply the Bernoulli's equation, straight forward you have to apply Bernoulli's equation. Bernoulli's equation is P1 by rho g plus V1 square by 2g plus Z1 is equal to P2 by rho g plus V2 square by 2g plus Z2 plus HF. What is P1 by rho g? That you have to find. V1 square by 2g, that is given as 6 square upon 2g plus Z1. Z1 is 5 plus y. 5 plus y. P2 by rho g, that is again PA by rho g plus y. Atmospheric pressure plus y. J2 is 0. V2 again 1.2 square upon rho g plus HF is 0.1. So all the values if you put, you will get P1 by rho g plus this value V1 square by 2g plus 5 plus y is equal to PA by rho g. P2 by rho g as PA by rho g plus y plus this V2 square by 2g plus Z2 is 0 plus HF is 0.1. So y will get cancelled. PA by rho g, you know, 10.3 meter of water. So if you take that 10.3 meter of water as a PA by rho g, you will get P1 by rho g as absolute value. Absolute value. So if you calculate P1 by rho g from this formula, you will get absolute value. So instead of taking 10.3 meter of water, they have taken PA by rho g as 0. Okay, 0. That means you will get gauge pressure. Gauge pressure. So P1 by rho g is coming as now minus. Okay, so here minus of 6.6616 meter is the P1 by rho g. So this shows that there is a negative sign, means that pressure is vacuum pressure head. So P1 by rho g is a vacuum pressure and negative pressure. Let us see the next numerical also. Indirectly you have to calculate the distance. Okay, here you have to calculate the pressure. Now if pressure is given, then you can calculate the distance also. A conical draft tube having diameter at the top as 2 meter and pressure head at 7 meter of water vacuum. So this is pressure is given. Discharges water at the outlet with a velocity of 1.2 meter per second at the rate of 25 meter cube per second. So velocity discharge is given, so you can calculate the velocity at other end also. If atmospheric pressure head is 10.3 meter of water and losses between inlet and outlet of the draft tubes are negligible, so HF is negligible. Find the length of the draft tube immersed in water, means Y. You have to find Y. Total length of the tube is 5 meter. So complete length of the tube is 5 meter. This complete length is given as 5 meter. So diameter D1 is 2 meter. P1 by rho g is minus 7 meter. Okay, so absolute pressure will be 10.3 minus 7. So it is 3.3 meter absolute. Okay, that difference you know. V2 is equal to 1.2 meter per second. Q discharge is 25 meter cube per second. HF is negligible, so neglect it. Total length of the tube is 5 meter and this Y distance. Okay, so HS. Okay, HS you have to find by the formula. Okay, we know the formula for P1 by rho g, or simply you apply the Bernoulli's equation between point 1 and 2. If you apply the Bernoulli's equation carefully between point 1 and 2, you should get P1 by rho g is equal to PA by rho g minus HS minus into bracket V1 square by 2g minus V2 square by 2g minus HF. HF is 0. Putting the values of V1 and V2. Okay, V1 you have calculated already, V2 is given. So all the values if you put P1 by rho g as absolute value 3.3 meter and PA by rho g, so you have to take now atmospheric pressure 10.3 because you have taken absolute value. If you have taken the negative value minus 7, okay, then you should not take it as a 10.3, you have to take it as a 0. Okay, so here this will give you HS value. So once you calculate HS, it is coming as 3.8464 meter. So after calculating HS, total length of the tube is given as 5 meter and HS you have calculated by applying the Bernoulli's equation between point 1 and 2. You can calculate Y because 5 is equal to HS plus Y. So y is equal to 5 minus hs, that is 5 minus 3.8464, which is coming as 1.1536 meters. So this is about the draft tube, theory of the draft tube. Okay, thank you.